The paper presents a novel approach to predict the solid-liquid phase boundary of molten salts, specifically sodium chloride, using thermodynamic integration (TI) and neural network potentials (NNPs), trained on density functional theory (DFT) data. This method combines the computational cost advantages of classical force fields with the accuracy of DFT, enabling first principles prediction of phase diagrams in molecular dynamics simulations. The study employs the Fumitosi potential for classical MD simulations, which is a rigid ion model that allows for rapid computation of interatomic forces but limits the accuracy of predicted properties to specific chemical environments and thermodynamic conditions used to parameterize the model. The authors also utilize neural networks as universal function approximators to describe the complex multidimensional potential energy surfaces of atomistic systems. They employ atom-centered symmetry functions, smooth overlap of atomic positions, SOAP, and neighbor list-based descriptors to generate features from atomic configurations, ensuring rotational, translational, and atomic permutation symmetries in the neural network. To predict the solid-liquid phase boundary, the authors use TI to calculate the free energy difference between the phases at various state points. A reversible pseudo-supercritical pathway is employed, which directly transforms the liquid to the solid phase, allowing for the calculation of the free energy difference by integrating the derivative of the interatomic potential energy with respect to the path parameter along the pathway. The paper highlights the sensitivity of the predicted phase boundaries to the choice of exchange correlation, XC, functional, with functionals that explicitly include dispersion interactions showing better agreement with experimental data over a wider range of temperatures and pressures. The Clausius-Clapeyron equation is then used to extend the phase boundary in the pressure-temperature space. The findings suggest that the choice of XC functional significantly influences the accuracy of the predicted phase boundaries, and those including dispersion interactions agree with experimental data more closely. This study demonstrates a method for predicting solid-liquid phase boundaries for any material at an ab-initio level of accuracy, with the majority of the computational cost at the level of classical potentials. This study focuses on the development of neural network potentials, NNPs, for sodium chloride, using various exchange correlation functionals. The aim is to accurately model both solid and molten phases across a wide range of temperatures and pressures. The authors utilize the simple in code for training and evaluating the neural networks, which are based on the atom-centered symmetry function approach. This method expresses the total energy as a sum of atomic energies, each expressed as a neural network of several symmetry functions evaluated on the local atomic configuration. The dataset for the NNP training consists of configurations extracted from ab-initio molecular dynamics (AIMD) simulations at various state points, including solid configurations in the stable rock salt and metastable cesium chloride and zinc blende structures near the melting temperature, and liquid configurations at ambient and high pressures. The authors validate the trained NNP by comparing its forces and energies to those generated via AIMD, and by comparing its radial distribution functions, RDFs, to those generated by the Fumitosi potential at 3 different state points. The results show that the energy errors are all within 26 MeV, atom, which is thermal energy at ambient temperature. The RDFs predicted by the NNPs appear to overlap with the Fumitosi potential in both the solid and liquid phases, indicating that each potential has learned the appropriate structure. A threefold cross-validation strategy is also implemented to assess the impact of training errors of each NNP on the final phase boundary results. The phase coexistence approach used in this study involves setting up an interface between a crystalline configuration and a liquid configuration and allowing the system to equilibrate at a specified state point. The authors test the direct interface coexistence method as an initial benchmark for the ambient pressure melting temperature of the Fumitosi potential and the NNP trained to the PBE functional. The resulting structures predicted by the NNPs are checked by running larger calculations with each potential on 4096 atom simulation cells of the solid and liquid phases at different state points. Here is a combined summary of pages 5 and 6 of the research paper. The authors discuss 2 approaches to predict the solid-liquid phase coexistence of materials: direct interface coexistence simulations and thermodynamic integration. In the former method, the system is set up with an interface between the solid and liquid phases, and the rate of change of the solid fraction is tracked as a function of temperature. However, this method has limitations due to the dependence on the orientation of the interface and the slow velocity of the interface close to the melting temperature. Alternatively, the authors employ thermodynamic integration to predict phase coexistence from the free energy difference between phases as a function of thermodynamic variables. This method involves constructing a reversible pathway between the two states, and the free energy difference is obtained using equation 2. The authors use a pseudo-supercritical pathway to obtain the free energy difference between the solid and liquid phases at a single state point, and then extend the phase boundary in the p-t space by integrating the Clausius-Clapeyron equation. The authors outline a three-step scheme for predicting the solid-liquid phase boundary of sodium chloride using neural network potentials, NNPs, trained to density functional theory, DFT. The first step involves using a pseudo-supercritical pathway with the Fumitosi potential to calculate the solid-liquid free energy difference as a function of temperature, increment GSL, T, to estimate the model's melting temperature, TFTM. The second step involves using a thermodynamic cycle involving thermodynamic integration from NNP to FT to obtain TNNPM. The third step involves extending the phase boundary, TM, by integrating the Clausius-Clapeyron equation. The authors detail the first step, which involves a four-step reversible pathway from liquid to solid at a single state point, displayed in Figure 3a. The pathway consists of deforming the liquid to the equilibrium volume of the solid, scaling down the Fumitosi interaction potential, switching on a tethering potential, and restoring the original potential. The resulting Helmholtz free energy curves for each step are shown in Figure 3b, and the Gibbs free energy difference, increment GSL, T, is obtained by repeating the pathway for several temperatures, as shown in Figure 3c. This study presents a novel approach to calculate the melting point of sodium chloride, using neural network potentials, NNPs, trained on density functional theory, DFT, data. The authors employ a pseudo-supercritical pathway to transform the Einstein solid to an ionic crystal, followed by a thermodynamic cycle that involves bulk transformations and pressure changes. This method allows for the estimation of the Gibbs free energy difference between the solid and liquid phases, which can be used to determine the melting point. The technique is demonstrated on NNPs trained to four different DFT exchange correlation functionals: PBE, PBE-Sol, PBED2, and PBED3. The results show that only dispersion-corrected functionals predict melting points that agree reasonably with experiment. In particular, the PBED2 variant exhibits the lowest error for the ambient pressure melting point, while the PBED3 variant shows better accuracy overall for the entire range of pressures considered. The study also highlights the limitations of classical potentials, such as the Fumitosi potential, which deviates from experimental measurements at higher pressures. The NNP-PBE potential underestimates the melting point due to its tendency to underestimate binding in solids, whereas the NNP-PBE-Sol potential improves upon this but still predicts lower melting points than experiment. The authors emphasize the importance of considering both the solid and liquid volumes near the melting point, as these contribute significantly to the accuracy of the phase boundary predictions. They also note that the relative underbinding of dispersion-corrected functionals for the perfect crystal becomes less important for solids at higher temperatures. This research paper presents a novel computational approach to predict the solid-liquid phase boundaries of molten salts using machine-learned potentials and thermodynamic integration. The study focuses on sodium chloride, as a model system, demonstrating the method's potential for predicting phase diagrams in single-component systems. The paper also discusses the importance of long-range dispersion interactions in DFT exchange correlation functionals for accurate melting point predictions, with PBED3 showing the highest accuracy among the functionals considered. The paper begins by discussing the relevance of molten salts in various industrial processes, including nuclear waste disposal and solar thermal energy storage. It then introduces the concept of neural network potentials, NNPs, and their use in thermodynamic integration for predicting phase boundaries. The authors emphasize the significance of the atomization energy of the crystal as a proxy for melting point prediction accuracy, while estimates based on lattice constants do not correlate as well. The paper also highlights the use of different DFT functionals, such as PBE, PBE-Sol, PBED2, and PBED3, in predicting solid-liquid phase boundaries. It is observed that the PBED3 functional yields the closest molar volumes and enthalpy differences compared to experimental values, correlating with its best accuracy for the phase boundary across the pressure-temperature space. The study employs a combination of machine learning and thermodynamic integration to efficiently predict ab-initio level solid-liquid phase boundaries in molten salts. This approach allows for the prediction of phase diagrams in single-component systems using any underlying first principles method. The paper concludes by discussing the potential of this method for future work on predicting phase diagrams of binary systems and solubility limits from first principles.